Hello everyone, welcome to another video where we're going to cover the details of an in-class problem. This time around, we're going to work with the probability mass function problem that says something like this. So we're asked to assume that we know somehow that 1 in 5 people have blue eyes. And then for the problem setup, we are told that we select 2 people at random. So we grab 2 strangers from the world and we are asked what is the probability mass function over n, where n is going to now be a variable that denotes the total count of blue-eyed people in my little sample of 2. So from the problem setup, we can distinguish 2 key pieces of information. The first one is that 1 in 5 people have blue eyes. And that could easily be translated as information about the probability of anybody in the world having blue eyes. So we would have here that P of B, where B is blue eyes, according to this problem setup, would be 1/5. And per the complement rule, we also know that the probability of someone not having blue eyes, anyone in the world, would, according to this problem setup, be 1 minus 1/5, so that is just 4/5. The second thing we can derive from the problem setup, because we only have observed 2 individuals at random from the world, is the possible values that n can have. So there are only 2 guys here, so we know that the maximum number of blue-eyed people that we can have in our sample is 2, right? And that can only happen when both guys have blue eyes. So there is only one possible scenario where that happens. On the opposite end, n equals 0, which is what would happen if neither of these 2 guys have blue eyes. And again, that can only happen in one scenario. They both come with not blue eyes. And in between, we have the possibility that only one of them has blue eyes. And that could happen in 2 different possible scenarios. One is if this is the guy that has the blue eyes, but not this guy. And the other one is if this is the guy that has blue eyes, but not this one. So there are 2 possible scenarios or 2 possible events that would lead to the exact same value of n. And we are going to have to keep that into account to solve this problem. And so the key instruction here is to evaluate the probability of each of these 3 possible scenarios. So let us start from the bottom up with the case in which neither of these 2 guys had blue eyes. So for this scenario where neither of them have blue eyes, this is equivalent of saying that this first guy that I'm going to denote X for simplicity has eyes that are not blue. And this second guy that I'm going to denote for simplicity Y also doesn't have blue eyes. So these 2 things happen at the same time. I have here my little AND notation. The other thing that I want to notice now is that these 2 guys were selected at random. There should not be any relationship between the color of the eyes of one of these guys and the color of the eyes of the other guy. We're going to treat them as independent results. And so if I want to judge the probability of n equals 0, which would be the probability of these 2 things happening at the same time, I know, using my special case of the product rule for independent cases, that this would be as simple as multiplying the probability that X has eyes that are not blue times the probability that Y also has eyes that are not blue. And we are given here by the problem setup, this probability is the probability of my eyes not being blue. So this is just 4/5 times 4/5. And I can solve that very quickly, numerator by numerator, denominator by denominator. So we know our first probability. Then we're going to move to the next case where the total number of people with blue eyes in my sample is just 1. And we note here that there are now 2 possible ways in which this could happen. This could happen if the guy X has blue eyes and the guy Y doesn't. So again, only X has blue eyes. Or, I'm using here my OR operator here, when X doesn't have blue eyes, but Y is the one that does. So in both these cases, only one of them has blue eyes. So it's still an n of 1, regardless of which of the 2 guys is the blue-eyed person. And now, again, the color of the eyes of each individual is independent of each other. So these are independent events. And more importantly, these 2 cases are possible cases that would lead to the same value of n, but they are mutually exclusive. So it is impossible for guy X to have blue eyes at the same time that he doesn't have blue eyes, as it is impossible for the Y guy to have not blue eyes and blue eyes at the same time. So these 2 scenarios are mutually exclusive. So let us now compute the probability of having exactly 1 guy with blue eyes in my sample. So let us compute the joint probability for the very first case where the X guy has blue eyes, but Y guy doesn't. So again, we talked that the color of the eyes of one guy should not have anything to do with the color of the eyes of the other. So these are independent events. This joint probability can be described by multiplying the probability of its marginal events. And then to this joint probability here, I'm going to add, because we said that we're mutually exclusive, the joint probability of now X guy having not blue eyes and Y guy having blue eyes. So this second joint probability that I have here. And again, because of the problem setup, we are given this information. So again, the probability of either X guy having blue eyes or Y guy having blue eyes is the same. It's just 1/5. And we know that the probability of Y guy not having blue eyes is the same as the probability of X guy not having blue eyes, which is just 1 minus 1/5 or 4/5. We multiply these marginals according to the product rule, and we end up getting the joint probability of X guy having blue eyes and Y guy not having blue eyes, and X guy not having blue eyes and Y guy having blue eyes. And we finally can add these two probabilities together because we said that these two events cannot be true at the same time. And we end up with a final probability estimate of 8/25. And we are now left with our last scenario where both guys have blue eyes, which again can only happen if both X guy has blue eyes at the same time that Y guy has blue eyes. So again, to judge the probability of n equal 2, we are simply going to multiply the probability of these two marginal events because, again, these are independent of each other. The color of the eyes of guy X has nothing to do with the color of the eyes of guy Y. And we are given these probabilities in the problem setup. So we know that here we end up with a probability estimate of 1/25. And now we have evaluated the probability for each possible outcome, and that is exactly what a probability mass function does. Let us state it together. So throughout this problem, we found that the probability of neither of the guys having blue eyes is 16/25. The probability that only one of these two guys have blue eyes is 8/25. And the probability that both guys have blue eyes is 1/25. This is our probability mass function. It describes the probability of every possible value that our variable n can have for this particular example. And as we can see, these values add up to 1, right? So we have 16 plus 8, that is 24, plus 1, that is 25, 25/25, that is just the entirety of the probability space that we had to distribute across all possible values of n. And that's it for this exercise.